If a space rock suddenly began to burn hotter than the surface of the sun, it sounds like a disaster movie trailer, but it's what three of the world's most advanced space observatories secretly recorded. On November 2nd, 2025, an interstellar object designated 3I/Atlas reached its perihelion, its closest point to our star. And instead of the expected gentle crimson glow, it erupted, a piercing, impossible blue. This wasn't just a surprise, it was a physical contradiction that shattered every known model of cometary science. This blue light was the signature of a staggering, unthinkable temperature, a temperature that, according to the laws of physics, this object simply could not have. And the moment the data was confirmed, everything we thought we knew about the universe, about what is possible and what is not, changed forever. To understand the crisis, you have to understand where this happened. From October 21st, 3I/Atlas vanished. It passed directly behind the solar disk, completely obscured from all telescopes on Earth. The task of watching it during this critical, invisible phase fell to an elite space-based network, SOHO, Stereo A, and the new GOE-19 satellite. These three solar sentinels, locked in precise non-Earth orbits, provided continuous overlapping coverage. SOHO delivered the essential white light imaging. Stereo A, leading Earth by over 20 degrees, gave the crucial off-angle view, allowing scientists to literally peer around the edge of the sun. And GOE-19, with its advanced CCOR1 coronagraph, captured the high-cadence multispectral imaging. They synchronized their clocks, they cross-calibrated their readings. Their data chain was robust, designed specifically to ensure not one detail was lost. And it was this triangulated, locked-in time perspective that allowed them to confirm the impossible event. The blue glow defies fundamental physics because the color of heat is governed by a simple rule, Wien's law. The hotter the object, the shorter the wavelength of its peak emission. Our sun's surface at 5800 Kelvin peaks close to yellow. For any passive object to appear blue purely by its own heat, it must be above 6000 Kelvin. But 3I/Atlas was 1.36 astronomical units out. At that distance, the solar constant, the absolute maximum energy available to heat the object, is about 770 watts per square meter. Even if this rock absorbed every single photon that hit it, the thermal equilibrium temperature for its surface should be far below 500 Kelvin. That is barely hot enough to boil water. It should glow deep in the infrared. Instead, the photometry from all three independent instruments confirmed a peak emission near 450 nanometers, a clear, deep blue dominance. This was not a subtle shift. It was a sustained, spatially extended envelope of blue light stretching nearly 300,000 kilometers across. The scale of the anomaly was as extraordinary as the temperature it implied. No known passive thermal process, no amount of solar heating, no rare chemical reaction can account for the creation of a massive envelope thousands of degrees hotter than predicted. The thermal budget was simply too small. The blue wasn't just surprising, it was physically extraordinary.
But the blue fire was only the opening chapter. As astronomers delved into the object's history and behavior, they began compiling a ledger of irregularities that strained the bounds of natural science. First, the trajectory. This was an interstellar visitor. These objects should arrive at random, steep angles, but 3I Atlas threaded the needle, flying within 5 degrees of the ecliptic, the very flat plane where all our planets orbit. It was a statistical impossibility for a random arrival. Second, sunward ejection. Normal comet activity, driven by sunlight and solar wind pressure, sends material streaming away from the sun. But coronagraphs captured repeated, persistent episodes of material blowing directly toward the solar glare. It was actively countering the physics of the solar wind. No known comet in history has ever shown sunward ejection at this scale. Third, water scarcity. Water is the dominant ice in virtually all comets, 80 to 90% by mass. 3I Atlas was composed of only 4% water. The rest was a strange exotic cocktail of carbon monoxide and other rare volatiles. Fourth, the engineered fingerprint. Spectroscopic analysis revealed an unusually high ratio of nickel to iron in the ejected dust. In our solar system, iron dominates, reflecting primordial chemistry. The nickel excess was more reminiscent of a refined, engineered alloy than of naturally formed ice or rock. The labs triple-checked the data. The result held. And fifth, the explosive growth. The luminous sheath didn't just turn blue, it ballooned to 300,000 kilometers in a nonlinear surge of brightness that simply could not be explained by standard dust-driven models. The activity was too energetic, too coherent, and occurred at a distance where the sun's influence was minimal. The combined evidence, low inclination, sunward ejection, engineered alloys, blue-hot emission, was too much to dismiss. Avi Loeb, a Harvard astrophysicist, formally added 3I Atlas to his catalog, revising his estimate for a technological origin to slightly above 4 out of 10. The debate had officially shifted from natural anomaly to something else entirely. The stakes were now clear, and that is exactly when the entire story went dark. On October 2nd, GOE-19's most advanced sensor captured a packet of high-resolution, multispectral images of the object near Perihelion. It was the key. The data that would either confirm a new physical process or offer a testable hint of technology. And almost immediately, it was classified. Intelligence agencies cited concerns over national technical means and sensor calibration. Representative Ela McAdams on the House Science Committee led the push for declassification, framing the issue as a fundamental test of public trust in science. While professional astronomers were locked out, citizen scientists around the world, armed with their own ground-based telescopes, pulled together what data they could through informal networks. It became a race against secrecy. The evidence for a paradigm-shattering discovery was hidden behind bureaucratic walls. As of today, we have no structured radio signals. We have no definitive infrared propulsion signature, but we have a blueprint for the truth. The final confrontation with 3I Atlas is already scheduled. On December 19, 2025, as the object nears Earth again, the most powerful eyes ever built, the James Webb Telescope, JWST, and the Hubble Telescope, HST, will execute a coordinated close-range observation campaign. They will gather 4 types of data with clear, falsifiable criteria. They will search for high signal-to-noise spectra, looking for structured emission lines, the telltale slopes of a non-natural heat source. They will use imaging polarimetry to distinguish natural fluffy cosmic dust from a potentially metallic or engineered surface. They will perform precision astrometry, tracking the object's path for any non-gravitational or controlled movement. And finally, they will use mid-infrared mapping, searching for any heat signature that cannot be explained by the weak light of the sun. Decisive outcomes rest on these benchmarks. Organized radio signals or abrupt, non-random trajectory shifts would support a technological explanation. Natural spectral bands and no infrared excess would favor a natural origin. For the first time, citizen scientists are globally synchronized with professional teams. The world is watching. 3I Atlas, the blue anomaly, forces us to confront the fact that an interstellar visitor can defy our core laws, not as a random outlier, but as a potential sign of intent. The object stands as the most anomalous body ever observed, reshaping how we prepare for the next visitor from the void. The central question persists. Does 3I Atlas represent unknown natural physics, a rare cosmic outlier, or evidence of technology? The answer will depend on data yet to come.